the idea that should not exist. Imagine a place in the universe where time seems to flow backward. A region of space-time where nothing can enter, yet matter, energy, and even light can escape. A cosmic phenomenon that is not observed, not confirmed, and yet stubbornly refuses to disappear from the equations of physics. This is the white hole, one of the strangest ideas ever proposed by human thought. To understand why white holes exist at all, we must begin with something far more familiar: black holes. Black holes are regions where gravity has become so intense that space-time itself collapses inward. Once something crosses the event horizon, it can never return. Every path forward leads deeper into darkness, toward a singularity where our known laws of physics break down. White holes are mathematically the exact opposite. If a black hole is a cosmic prison, a white hole would be a cosmic fountain. Nothing can cross into it. No particle, no photon, no signal from the outside universe is allowed entry. Instead, it only emits. Matter bursts outward. Energy spills into space. Light escapes freely, but can never be traced back inside. The idea feels unnatural. The universe we observe is governed by entropy, the tendency of systems to move from order to disorder. White holes do the opposite. They appear to violate the arrow of time itself. And yet, when physicists solved Einstein's equations of general relativity, white holes emerged naturally as valid solutions. They were not invented to be exotic. They appeared because the mathematics demanded symmetry. In 1916, Carl Schwarzschild found the first exact solution to Einstein's field equations, describing what we now call a black hole. But hidden within that solution was something unexpected. When extended fully, the equations didn't describe just a collapsing object, but a space-time with two distinct regions. One region allowed matter to fall inward forever. The other allowed matter to emerge, but never enter. This second region was the white hole. For decades, physicists largely ignored it. Black holes had clear formation mechanisms: collapsing stars, merging remnants, extreme gravity. White holes had no obvious origin. No known process in the universe could create one. There was no stellar collapse that resulted in a white hole. No explosion that neatly produced a one-way exit for matter. And yet, the equations refuse to erase them. White holes exist in what is known as maximally extended space-time. When physicists extend a black hole solution beyond what a real star produces, they find a strange cosmic bridge connecting two regions of space-time. On one side, matter falls, and this is the black hole. On the other side, matter flows out, this is the white hole. The two are connected through a theoretical structure known as an Einstein-Rosen bridge, or more popularly, a wormhole. But there is a catch. This wormhole is not stable. It collapses faster than light could cross it. Nothing can pass through from one side to the other. The white hole does not act as a doorway. It acts as a boundary one that only allows escape, never entry. This raises a disturbing question. If white holes exist, where does the matter they emit come from? In the mathematics, the answer is unsettling. The matter does not come from our universe. It emerges from the past singularity of space-time itself. In simple terms, the white hole has no history we can observe. It appears already ejecting matter with no visible cause. It violates our instinctive demand for causality. Physicists call this a naked initial condition. Something simply is without explanation. This alone makes white holes deeply uncomfortable for science. Modern physics relies on predictability. Causes precede effects. White holes reverse that logic. They appear as effects without causes, cosmic anomalies that defy the very structure of explanation. And yet, there's another problem, even more devastating. White holes are violently unstable. Any tiny disturbance, one stray particle, one quantum fluctuation, one ripple in space-time would immediately collapse the white hole. The universe is not a quiet place. Space is filled with radiation, particles, and vacuum fluctuations. A white hole, if it formed, would be destroyed almost instantly. This instability is not a small inconvenience. It is fatal. According to classical physics, white holes cannot survive long enough to be observed. They are mathematical ghost solutions that exist on paper, but not in reality. Many physicists consider them artifacts of idealized equations, not genuine objects of the cosmos. But here is where the story takes a turn. Physics does not end with classical equations. When quantum mechanics enters the picture, the certainty of white holes being impossible begins to erode. Some theories suggest that white holes may not exist as permanent structures, but as fleeting, microscopic events. Others suggest they may appear only under extreme conditions, such as the final moments of a black hole's evaporation. If black holes can shrink and disappear through Hawking radiation, what happens at the end? Does information vanish forever, or does something else emerge? Some physicists propose an extraordinary idea, that the death of a black hole could give birth to a white hole, not a mirror image in space, but in time. In this view, a white hole is not a separate object, but the final echo of a black hole's life. Matter that once fell and does not disappear. It waits, and after unimaginable spans of time, it re-emerges in a sudden release, a white hole explosion. If this is true, white holes are not forbidden by reality. They are simply rare beyond comprehension. And that possibility changes everything. Here are some questions to be answered. How quantum gravity resurrects white holes. Why some scientists believe they may already be hiding in the universe. And how these impossible objects could solve one of the greatest mysteries. In physics, the fate of information itself. When quantum physics refuses to let go. Classical physics is ruthless with white holes. It allows them to exist on paper, but nowhere else. The moment the real universe intrudes radiation, particles, noise, the white hole collapses. End of story. But physics did not stop evolving in the 20th century. When quantum mechanics enters the picture, the universe stops behaving politely. Certainty dissolves. Absolute boundaries blur. And ideas once dismissed as impossible begin to reappear, not as fantasies, but as consequences. The turning point came when physicists realized something deeply troubling. Black holes should not be silent forever. In the 1970s, Stephen Hawking discovered that black holes are not completely black. At the quantum level, empty space is not empty. It seethes with fluctuations, pairs of particles and antiparticles constantly appearing and annihilating. Near a black hole's event horizon, these fluctuations become distorted. One particle falls in, the other escapes. From the outside, the black hole appears to glow. This glow, now called Hawking radiation, means black holes lose mass over time. Slowly, incredibly slowly, but inevitably. Given enough time, even the largest black hole will evaporate. This created a crisis. If a black hole evaporates completely, what happens to the information about everything that fell inside it? According to quantum mechanics, information cannot be destroyed. But classical black holes swallow information forever. This contradiction became known as the black hole information paradox. And for decades, it haunted physics. White holes re-enter the story here not as curiosities, but as potential solutions. One radical idea suggests that a black hole does not end in nothingness. Instead, it undergoes a transformation. When the black hole shrinks to an extremely small size, quantum gravity effects take over. The collapse halts. The singularity is avoided, and space-time rebounds. What emerges is not another black hole. It is a white hole. In this scenario, matter does not vanish. It is delayed. Everything that ever fell into the black hole remains trapped in a quantum gravitational state, frozen from the outside perspective. To the universe, the black hole evaporates quietly over immense time. But inside, time behaves differently. When the transition occurs, the trapped matter is released. Not gently, not gradually. In a violent outburst, a white hole eruption. From the outside, this release might appear as a sudden burst of energy from an otherwise empty region of space. No warning, no precursor, just an explosion that seems to have no cause. Theoretical physicist Carlo Rovelli and others working on loop quantum gravity have explored this idea in detail. In their models, space-time itself has a granular structure at the smallest scales. When gravity becomes too intense, it does not create an infinite singularity. Instead, it creates pressure like a compressed spring. Eventually, that pressure forces space-time to bounce. Black hole to white hole. The timescale of this bounce is strange. For the infalling matter, the transition happens quickly. But for an outside observer, it could take longer than the current age of the universe. A black hole formed billions of years ago could be on the verge of becoming a white hole today or in trillions of years. This leads to a disturbing implication. White holes could exist right now as remnants of ancient black holes, tiny, dense objects releasing energy extremely slowly or waiting to release it all at once. But if that's true, why haven't we seen them? The answer may lie in how subtle their signatures are. Unlike black holes, white holes do not accrete matter. They do not bend surrounding material into glowing disks. They do not announce themselves through gravitational capture. They are silent until the moment they are not. Some physicists speculate that fast radio bursts brief. Intense flashes of radio energy from distant galaxies could be linked to white hole events. Others suggest gamma ray bursts or unexplained cosmic explosions might be white hole emissions. These ideas remain speculative. No confirmed observation exists. Yet the fact that white holes are even being discussed seriously marks a shift in physics. Once dismissed entirely, they are now considered possible outcomes of quantum gravity. There is another twist. If white holes release information that was once trapped, they may preserve the fundamental laws of quantum mechanics. Information is not lost. It is delayed beyond comprehension. The universe remembers everything, it just does not reveal it on human timescales. This reframes white holes not as violations of physics, but as guardians of its consistency. But this solution comes at a cost. White holes still violate our sense of causality. They appear to release matter without any observable cause in our timeline. They look like explosions with no source. They challenge the idea that the universe is locally predictable. And perhaps most unsettling of all, they suggest that time itself is not as one-directional as we believe. If black holes are the future of collapsing matter, white holes may be its past or its echo. They blur the distinction between beginning and end, between cause and effect. Now, we will explore whether white holes could actually be detected, what signal scientists are searching for, and how the universe might already be whispering their existence through unexplained cosmic phenomena. If white holes exist, they're not the kind of objects that make themselves easy to find. Black holes announce their presence by destruction. They tear stars apart, heat matter to billions of degrees, and carve luminous scars into space. White holes, by contrast, are defined by absence. They do not pull. They do not feed. They do not grow. They wait. This creates a brutal challenge for observational astronomy. Nearly every tool we use to study the universe relies on interaction. We observe light that has been emitted, reflected, or distorted. We detect objects by how they influence their surroundings. A white hole refuses all of that. Nothing falls in. Nothing lingers nearby. Until the moment it releases something, it is effectively invisible. So how do you find an object that does nothing until suddenly it does everything? The search for white holes begins not with certainty, but with anomalies. Across the universe, astronomers observe events that defy easy explanation. Bursts of energy that last milliseconds. Explosions that appear in empty regions of space. Signals that carry immense power but leave no remnants behind. These phenomena are rare, unpredictable, and difficult to trace. One of the most intriguing examples is the fast radio burst. These are brief flashes of radio waves, lasting only fractions of a second, yet releasing as much energy as the sun emits over days or even weeks. Some repeat. Others occur once and never again. Many originate from distant galaxies. A few come from regions with no obvious energetic source. Standard astrophysical explanations exist. Magnetars, neutron star collisions, and extreme plasma environments can produce powerful radio emissions. But not all fast radio bursts fit neatly into these categories. Some appear too clean, too isolated, too sudden. This has led a small but growing number of physicists to ask a dangerous question. What if some of these bursts are not caused by something exploding, but by something releasing what it was never allowed to keep? In white hole models connected to black hole evaporation, the release of trapped matter is sudden and intense. Information that fell in over millions or billions of years is expelled in short bursts. The energy would be concentrated. The event would be brief. And afterward, there would be nothing left to observe. No accretion disk. No expanding set. Nearly every tool we use to study the universe relies on interaction. We observe light that has been emitted, reflected, or distorted. We detect objects by how they influence their surroundings. A white hole refuses all of that. Nothing falls in. Nothing lingers nearby. Until the moment it releases something, it is effectively invisible. So how do you find an object that does nothing until suddenly it does everything? The search for white holes begins not with certainty, but with anomalies. Across the universe, astronomers observe events that defy easy explanation. Bursts of energy that last milliseconds. Explosions that appear in empty regions of space. Signals that carry immense power but leave no remnants behind. These phenomena are rare, unpredictable, and difficult to trace. One of the most intriguing examples is the fast radio burst. These are brief flashes of radio waves, lasting only fractions of a second, yet releasing as much energy as the sun emits over days or even weeks. Some repeat. Others occur once and never again. Many originate from distant galaxies. A few come from regions with no obvious energetic source. Standard astrophysical explanations exist. Magnetars, neutron star collisions, and extreme plasma environments can produce powerful radio emissions. But not all fast radio bursts fit neatly into these categories. Some appear too clean, too isolated, too sudden. This has led a small but growing number of physicists to ask a dangerous question. What if some of these bursts are not caused by something exploding, but by something releasing what it was never allowed to keep? In white hole models connected to black hole evaporation, the release of trapped matter is sudden and intense. Information that fell in over millions or billions of years is expelled in short bursts. The energy would be concentrated. The event would be brief. And afterward, there would be nothing left to observe. No accretion disk. No expanding set. No gravitational signature beyond the moment itself. Just a flash. Another possible signal lies in gamma ray bursts. These are among the most powerful explosions known, capable of sterilizing planets from across galaxies. Most gamma ray bursts are linked to massive star collapse or neutron star mergers. But a small subset defies classification. They occur in regions with no massive stars. They leave no visible remnants. They do not match existing models. Again, white holes are not the favored explanation, but they're no longer unthinkable. There's also a subtler possibility. White hole remnants, according to some quantum gravity theories, may not explode dramatically at all. Instead, they may persist as tiny, stable objects, slowly releasing information over immense time. These remnants would be extremely dense, extremely small, and nearly impossible to detect directly. Some physicists have suggested that dark matter itself could be composed of such remnants. Objects that interact gravitationally, but emit almost nothing. Objects that do not absorb matter, but also do not vanish. Objects that are not black holes, yet not ordinary matter. If true, the universe could be filled with the fossilized echoes of black holes long gone. But evidence remains elusive. The problem is not just technological. It is conceptual. White holes challenge the way we interpret observations. Astronomers are trained to look for structures, sources, and processes that evolve over time. White holes do not evolve in the usual sense. They appear and disappear, or they persist without interaction. Even if we observed one, we might not recognize it. Gravitational waves offer another possible path. When massive objects merge or collapse, they send ripples through space-time. These waves carry information about their source. If a white hole transition occurred, it might produce a unique gravitational wave signature, unlike anything from black hole mergers. So far, no such signal has been identified, but gravitational wave astronomy is still young. We have only been listening to the universe for a brief moment. The deeper issue is that white holes may not belong to the universe of stars and galaxies at all. They may belong to the universe of extremes, of singular moments, of boundaries between classical physics and quantum reality. This places them at the edge of testability. Science demands evidence. White holes offer mostly silence. Yet history shows that silence does not always mean absence. Black holes themselves were once dismissed as mathematical absurdities. For decades, they were thought to be unphysical, too extreme, too perfect, too strange to exist in nature. Today, we photograph them. White holes may be following the same path, not from fantasy to confirmation, but from impossibility to uncertainty, from dismissal to cautious curiosity. Now, we will confront the hardest question of all, not whether white holes exist, but whether they can exist without breaking the universe. We will examine causality, time symmetry, entropy, and the uncomfortable possibility that reality is far stranger than our intuition allows. The deepest problem with white holes is not observational. It is philosophical. A white hole does not merely challenge our instruments. It challenges the structure of reality itself. At the heart of physics lies a simple assumption: causes come before effects. This principle is so deeply embedded in science that we rarely question it. Even in quantum mechanics, where randomness rules outcomes, the sequence of events remains intact. A measurement happens. A result follows. White holes break this order. A white hole emits matter and energy without any observable cause in the past of our universe. There is no collapsing star, no buildup of pressure, no warning signs. The emission simply happens. To an external observer, it appears as a violation of causality. This is not a small issue. Causality is what allows prediction, explanation, and scientific understanding. Without it, physics becomes storytelling. Defenders of white holes argue that causality is not violated, only misunderstood. In their view, the cause of a white hole's emission lies outside our accessible timeline. The matter was once inside a black hole. The process unfolded over immense spans of time, distorted by extreme gravity. What looks like an effect without cause is really a delayed consequence of a long-forgotten collapse. Time, in general relativity, is not universal. It bends. It stretches. Near a black hole, time slows dramatically. What takes seconds for falling matter may take billions of years for the outside universe. When quantum gravity is added, time may lose its classical meaning altogether. From this perspective, a white hole is not a violation of time's arrow. It is a loop in it. But this explanation introduces another problem: entropy. The second law of thermodynamics states that entropy increases. Systems evolve from order to disorder. Black holes obey this law. In fact, they represent the maximum entropy state for a given amount of mass. When matter falls into a black hole, entropy increases. White holes appear to reverse this process. They eject matter in a highly ordered way. They decrease entropy locally. This should not happen. Physicists respond by pointing out that entropy can decrease locally as long as it increases globally. A refrigerator does this every day. But the scale of a white hole is not domestic. It is cosmic. The entropy decrease would be enormous. Some theories argue that the entropy was already accounted for during the black hole phase. The information was not destroyed, only hidden. When the white hole releases it, the total entropy of a universe still increases across the full history of the process. This explanation is mathematically consistent. Whether it is physically satisfying is another matter. Then there is stability. Classical white holes are catastrophically unstable. Any interaction destroys them. Quantum models attempt to bypass this by making white holes extremely small or extremely brief. A white hole that exists for a fraction of a second, or one that is isolated by quantum effects, may avoid classical instability. But this raises an uncomfortable possibility. If white holes exist only as microscopic or transient events, are they meaningful objects at all? Or are they simply transitions, like quantum tunneling, that do not deserve the title of cosmic structure? This debate cuts deep. It forces physicists to confront what it means for something to exist. Is existence defined by longevity? By observability? By mathematical consistency? Black holes exist even when we cannot see them. Do white holes deserve the same status? Another unsettling implication concerns determinism. If white holes release matter unpredictably, they introduce randomness into the large-scale universe. Not quantum randomness, but macroscopic unpredictability. Events with no precursor. Explosions with no warning. This threatens the idea that the universe is, at some level, predictable. Some physicists find this unacceptable. Others find it liberating. There is also the question of time symmetry. The fundamental equations of physics, excluding thermodynamics, are mostly time reversible. They do not care whether time moves forward or backward. White holes restore symmetry to gravity. If black holes exist as sinks of matter, white holes act as sources. The universe we observe, however, is not symmetric. It has a clear arrow of time. White holes may be mathematically natural, but cosmologically forbidden, unless the arrow of time itself is emergent. Some theories suggest that time's direction arises from initial conditions, not fundamental laws. If so, white holes may exist in regions or epochs where those conditions differ, or they may represent boundary conditions at the edges of space-time, not objects within it. This leads to a final, disturbing thought. White holes may not be things in the universe. They may be features of a universe's beginning or end, echoes of creation, or signals of a cosmic reset. Now, we will step back and ask the ultimate question. Are white holes real, or are they mirrors held up by mathematics, reflecting our ignorance back at us? And what does their possible existence tell us about the limits of human understanding? White holes occupy a strange place in science. They're not observed. They are not required. And yet, they refuse to disappear. They exist at the intersection of mathematics, philosophy, and the limits of knowledge. Every attempt to banish them seems to leave something unfinished, something unresolved. This alone makes them important. Physics has a long history of uncomfortable ideas that turn out to be real. Black holes themselves were once considered absurd. Time dilation was mocked. Gravitational waves were doubted. Reality has a habit of exceeding intuition. White holes may simply be the next reminder, or they may be warnings. One interpretation is that white holes are artifacts of idealized equations. When we extend mathematical solutions beyond physical relevance, we sometimes encounter structures that look meaningful but are not. In this view, white holes are like negative distances or imaginary times. Useful in calculation, meaningless in nature. This interpretation is appealing because it preserves the universe we think we understand. It avoids causality violations. It protects the arrow of time. It keeps entropy moving in one direction. But it comes at a cost. If white holes are discarded, the information paradox remains unresolved or must be solved by other means. The universe becomes a place where information can disappear forever, violating the principles of quantum mechanics. Many physicists find this unacceptable. Another interpretation is more radical. White holes may be rare, subtle, and almost impossible to observe, but still real. They may occur only at the end of black hole lifetimes, on timescales far beyond human history. They may be microscopic. They may masquerade as unexplained bursts of energy or dark remnants drifting silently through space. In this view, white holes are not dramatic opposites of black holes. They are quiet conclusions, the universe's way of returning what it once hid. There's also a deeper possibility. White holes may tell us that space-time itself is incomplete as we understand it. that gravity, quantum mechanics, and time are not separate concepts, but facets of a deeper structure we have not yet uncovered. White holes may not be objects, but transitions. Not places, but processes. They may represent the moment when space-time changes phase. If this is true, then asking whether white holes exist may be the wrong question. The right question may be whether our definitions of existence are sufficient. Science advances not only by discovery, but by confrontation. White holes confront us with our assumptions about cause and effect, about time and irreversibility, about what can and cannot be known. They force us to admit that our most trusted theories disagree at the extremes. This is not failure. It is progress. Every major breakthrough in physics began with contradictions that refuse to go away. White holes may be such a contradiction, a sign that we are approaching the limits of current understanding. Whether they are ever observed may not even matter. Their role may be to guide theory, not observation, to point toward a future framework where black holes, quantum information, and space-time geometry coexist without paradox. In the end, white holes remain what they have always been. Not monsters lurking in the cosmos. Not gateways to other universes. Not fountains of creation. They are mirrors. They reflect our questions back at us. About time, about knowledge, about whether the universe is obligated to make sense to creatures who only experience a tiny slice of it. If black holes represent the darkness of the unknown, white holes represent the blinding edge of explanation, where answers emerge without context, where effects appear without visible causes, where reality stops reassuring us. Perhaps that is why white holes unsettle us more than black holes ever did. Darkness can be explored, silence can be measured, but a universe that answers without explaining challenges the very foundation of understanding. And maybe that is the final lesson of white holes. Not that the universe is stranger than we imagine, but that it may be stranger than we are capable of imagining at all. White holes remain one of the most unsettling ideas in modern physics because they sit precisely where certainty ends. They are not simply mysterious objects waiting to be discovered with better telescopes. They are challenges to the way reality is structured in our minds. Every attempt to understand them forces us to question assumptions so fundamental that we rarely notice we are making them at all. At first glance, white holes appear absurd. Objects that eject matter but never accept it. Events that seem to occur without causes. Structures that reverse the familiar flow of time and entropy. In a universe that appears relentlessly one-directional, white holes feel like mistakes. Yet they do not arise from careless thinking. They emerge from the same equations that accurately describe planets, stars, galaxies, and black holes. The mathematics that predicts gravitational waves and the bending of light also allows white holes. To reject them outright is to claim that nature selectively obeys its own rules. This creates a tension that has never been fully resolved. If white holes are impossible, then our most successful theory of gravity is incomplete in a profound way. If white holes are possible, then our understanding of time, causality, and information is deeply flawed. Either way, something fundamental is missing. What makes white holes especially important is not whether they exist as physical objects, but what they reveal about the boundaries of theory. They expose the fracture between general relativity and quantum mechanics more clearly than almost any other concept. Black holes already strain this divide. White holes push it beyond breaking. They also force us to confront the nature of explanation itself. Science is built on tracing effects back to causes. White holes invert this logic, presenting outcomes without accessible histories. They ask whether every event must be explainable within our observable past, or whether some processes unfold on scales so extreme that causality becomes unrecognizable. In this sense, white holes may be less about the universe and more about us, about the limits of human intuition, about our discomfort with answers that do not come packaged with reasons we can grasp. There's also a humbling lesson here. The universe does not owe us simplicity. It does not promise that reality will align with how our brains evolved to understand it. Concepts like before and after, inside and outside, cause and effect may be approximations, useful in daily life but fragile at cosmic extremes. White holes sit at those extremes. They remind us that physics is not a completed story, that even the most successful theories are provisional, that what we call impossible today may become inevitable tomorrow once the right framework is found. Whether white holes ultimately exist as real phenomena, transient transitions, or purely mathematical boundaries, their role is already significant. They mark the edges of knowledge. They illuminate where our current ideas fail. And they hint that time, information, and space-time itself may be far stranger than our current language allows. In confronting white holes, physics is not chasing monsters in the dark. It is listening to the echoes of unanswered questions. Questions about where information goes, about whether time can truly be reversed, about whether the universe has beginnings and endings, or only transformations we do not yet understand. The true value of white holes may lie not in discovery, but in discomfort. They force theory to evolve. They prevent complacency. They remind us that understanding the universe is not about reaching final answers, but about refining better questions. And perhaps that is their quiet purpose. Not to exist as spectacular objects in the sky, but to exist as signposts at the frontier of thought, pointing toward a deeper, unfinished truth that still waits beyond the horizon of what we know.